Hi, I'm Juha and I'm a hockey player here at USC. I will be going through some physics concepts and examples with you this semester. And remember, just like on the ice, there's no such thing as luck in physics. Just keep your head up and work hard.
Let's study acceleration in rotational motion in the case when we have a car that is driving along a curved path with the radius of curvature being 300 meters and its initial speed is 20 meters per second, and it starts braking in such a way that it comes to a complete halt in 100 meters. We would like to know the magnitude of acceleration in the beginning and in the end. And we are assuming constant acceleration during this maneuver. So in that case, we can resort to our cheat sheet, and here it is. So what are we after? For the total acceleration, we need two components. We need the radial and tangential acceleration. And the acceleration in the tangential direction can be solved from what we have using this equation, because we know initial and final velocities, and we know the distance covered in that case. So we just solve for the ax from here, or we just denote it as because it's along the arc s. So going from there, first of all, the final velocity vx is 0, so we just have 0 equals initial velocity squared plus 2 times the constant acceleration in s direction along the arc, multiplied by the final position minus initial position, so that is just a change in distance, so that's going to be delta s. And from here we solve the constant acceleration term in the tangential direction, and let's make that notation. So as is same as a tan, and we get minus v initial squared divided by 2 times delta s. And initial was 20 meters per second squared divided by 2 times 100 meters. So we get that's 400 divided by 200. So that's 2, and units are meters. So that's going to be meters squared. Oh, there's a mistake. So that's not going to be second power. So meter squared second squared divided by meter. So we are left with second squared, meters per second squared, which is the unit of acceleration. So we're good with that, and it's of course of negative sign because we're braking. Hence our velocity in the tangential direction is increasing at a constant rate, 2 meters per second squared. What about the radial direction then? So expression for the radial acceleration is v squared divided by r. And now we see that this changes because it's a function of velocity that goes from 20 meters per second to 0. So let's have two options, or two values, initial and final. So a rad, calculate initial first, that's going to be v initial squared divided by r. So 20 meters per second squared divided by the radius of curvature. So that's going to be 400 divided by 300, 1.33, again meters per second squared. And the radial acceleration at the final moment when we have 0 velocity, well, that's going to be only just 0, because v at that point will be 0. And then the total accelerations, so the magnitude of the total acceleration vector is by Pythagorean theorem. Again, so for example, in the initial case we have tangential component this way, and then the radial component perpendicular to it. So their total sum would be looking something like this. That's a total. And the magnitude is using Pythagorean theorem. So tangential component squared, so minus 2 meters per second squared, plus the radial squared. And that's going to be squared as well. We get about 2.4 meters per second squared. And so this is initial and final. Well, we only have the tangential component, so the magnitude is just the magnitude of that one, so a little bit less, 2 meters per second squared. And so we see that in the final moment we only have the tangential component, so that's going to be our A final, and it's directed, or is tangential of course, to the direction of movement. Whereas in the initial phase, initial time, we had the radial component that will deviate the direction of the total acceleration vector a little bit towards the center.